So this theorem is so important that is called fundamental. And in calculus, we have two concepts, differentiation and integration. And fundamental theorem of calculus connects these two concepts. So let's review a bit for differentiation and integration. You know about differentiation as the slope of a tangent line. If you have a function f, so in the whole lecture we consider f as a continuous function. Let's say we work with x between a and b. So here I have a graph of f. And say we have a point here. X equal to, say, x naught. Then f prime of x at x naught is the slope of the tangent line of the graph of f of x at the point x equal to x naught. Y equal to f of x. This point is a point of coordinates x naught, f of x naught. And f prime at x0, the slope of the tangent line. Of y equal to f of x at x equal to x0. And this is the limit, say 8 tends to 0. F of x naught plus 8 minus f of x naught divided by 8. In some book we can see them write as delta x. 10 to 0 delta x for 8 over delta x. So this is the derivative. So we have differentiation. Now about integration. Let's talk about definite integral. Say we have this integral from a to b, f of x dx. Let me graph f. Say for example, this is our graph, f y equal to f of x. So f is continuous. Y equal to f of x. Say from x from a to b. And this one, integral from a to b, f of x dx, is actually the area under the curve. Y equal to f of x. In this picture, I just draw it simple, so it's the curve above the x-axis. But you can also draw that like this. Can be either above or below. So to make it simple, let me just draw it like this. So here we have three regions. Here's y equal to f of x. X between a and b. A, b, y equal to f of x. The integral from a to b, f of x dx, is the area under the curve. So this region and this region. So we have two regions above the x-axis, one region below. Let me call this region 1, 2, and 3. This is the area of region 1 minus area of the region 2 plus area of the region 3. So above the x-axis, this region has positive area. So we think of that integral from A to, say, C. Area of the region 1. Integral A to C. F of x dx. And now C, let me call it D. C to D. Integral from C to D. F of x dx equal to minus the area of 2. So area under the curve, but here this region is above the curve, not under the curve. So that's why we have minus. And integral from D to B, f of x dx is area of region 3. Yeah, so that's about the review for differentiation and integration. Now we will state the main theorem, the fundamental theorem of calculus. There are two parts for the fundamental theorem of calculus. Part 1. And in both parts we need f. So let f of t or f of x. So let f be a continuous function. Say we are working with the closed interval on the closed interval AB. And to make it simple, the result is true for any continuous f on the closed interval AB. So I will just do it for this picture. Y equal to f of x, and I draw it above the x-axis, so that the idea when we write out the proof is simple to just explain it this way. It is true for all continuous function on a closed interval AB. So here's f of x, here's a, b. Part 1 is this. Now say let a of x, big A of x, be the integral from a to x. So this a of x is a function in x, integral from a to x. So for each value of x, you have one values for xa, f of t dt. So this is a integral of the function f of t. So integral of f of t dt, t run from a to x. So how do we think about this? A to x. So let's say now we want, because x now say for each value of x fixed, t run between a and x. So let me copy this picture. And we work for t run between a and x. For any given x, you have one a of x. So let's say this is f of t, t between a and x between a and b, so x here. So instead of considering the whole thing, I just consider the integral f of t a of x, a to x, f of t dt. So this means we only look at the area under the curve f of t run between a and x. So we only look at the area of this region, area of the region 1 here. Now we have a of x. The theorem says that then a of x is an antiderivative of f of x. So this is to say that this means a prime of x equal to f of x. And if you want to write a bit further, this means if I write out all in one formula, this means the derivative with respect to x of the function a of x is this one. So integral from a to x f of t dt equal to f of x. So this is a statement of part 1 of the fundamental theorem of calculus. You always need this assumption: f must be continuous on the interval AB. The statement for part 1 is this. Now you see that this one link the relation between differentiation and integration. So the derivative of the integral give us back the function f. The derivative of the integral of f give us back f. Let me state the second part of the theorem and then we try to understand why it's true. Part 2 of the theorem. Again, remember that I still have the function f continuous on AB. Part 2 say that the integral of a and b, it helps us to compute this integral, saying f of t dt. So remember that when we learn about the area under the curve, this is the area under the curve f of t between a and b. So area of the whole thing here. Area under the curve. We need to decompose that into very thin rectangles. Take the sum, put the limit of the Riemann sum, right? And then we let the limit of n tend to 0 with n such rectangle to compute the Riemann sum. And that one gives us the answer for the area under the curve. So we don't want to do that n every time. To compute the area under this curve, we don't want to do a partition of AB, compute the area of those rectangles, compute the Riemann sum, take the limit, compute the limit. This theorem, fundamental theorem of calculus, part 2 say that if capital F of x is an antiderivative of small f of x, then we can just compute this integral by f b minus f a. And you know what? This f, you can choose any antiderivative of small f you want. Because this is the second part of the fundamental theorem of calculus. Now let's try to prove both parts of the theorem, or at least I give the ideas why it should be true. Let's do the first one. Part 1, a of x equal to this, and we need to show that a prime of x equal to f of x. Idea, a proof of part 1. So let's do part 1. A of x integral from a to x f of t dt. As we said, this is the area under the curve. This one, area of this region. We need to show that a of x is an antiderivative of f. So this means we need to show that a prime of x equal to f of x. So let's do that by definition. We will write down what a prime of x is, and we will prove that equal to f of x. A prime of x, by definition of derivative, this is the limit of a x plus 8 minus a of x divided by 8, let 8 tend to 0. That's what we reviewed at the beginning. Now let's look at this term and this term. A of x, as we said, a of x is the area of region 1. A of x plus 8, so say 8 is a tiny bit here, so x plus 8 is this point. Then we have this point is a point correspond to x plus 8. So this point has a coordinate x plus 8, f of x plus 8. And the other point here correspond to x, f of x. So this one is area under the curve for x run between a and x plus 8. So the area of this region. You extend this a bit, this region up until here, minus the area of region 1. And what we really get after we compute this area minus this area is the area of this tiny part here. This is the numerator. A x plus 8 minus a of x is the area of this very thin, and we can think of that as a rectangle when we let it tend to 0. So this, the width of the rectangle here is 8. This length here is f of x, and the other one here f of x plus 8. When 8 tends to 0, we can think of that as a rectangle. The width of the rectangle is 8. The height of the rectangle is f of x. F is continuous, so that's why f of x is very close. F of x plus 8 is very close to f of x, and it tends to f of x when it tends to 0. That is the reason why we need f is continuous. Now the area is the width times the height. So this one gives us area equal to 8 times f of x. That is the numerator. Now the whole thing becomes limit 8 tends to 0, 8 times f of x divided by 8, which is limit f of x, 8 tends to 0, which is f of x. So you see that we did show that a prime of x is f of x. So a of x is an antiderivative of f of x, which we finished the first part of the theorem. we did show part 1 of the theorem. A is an antiderivative of f of x, which is a prime of x equal to f of x, or written equivalently d over dx, this interval equal to f of x. Now let us prove the second part. Let f of x be an arbitrary antiderivative of small f of x. We need to show that. Here, how I could do. I compute this one, and then I try to show that it's equal to this interval. Proof part 2. So we know that f of x is an antiderivative of small f of x. But part 1 also tells us that a of x is also an antiderivative of f of x. Both of the function big F of x and big A of x are antiderivatives of small f of x. And we know that antiderivatives of the same function differ by a constant. So this means f of x equal to a of x plus a constant c. So they differ by one constant c. Now we need to show that interval from a to b, f of t dt equal to f of b minus f of a. Let's compute that. We have f of x here by this formula. I compute f of b, I compute f of a. So f of b minus f of a equal to f of b equal to a of b plus c. So that's for the first part, a of b plus c. The second part, a of a plus c. C minus c just cancel out. A of b is the integral from a to b f of t dt. A of a, integral from a to a f of t dt. Thus I use the definition of a of x, this one, by definition of a of x. Thus a of x is defined as integral from a to x f of t dt. So we just plug in a of b equal to integral from a to b, a of a integral from a to a. Integral from a to a, or you think of the area under the curve where t runs from a to a. So that's nothing, it's 0 here. So that's why this one equal to integral from a to b f of t dt minus 0, which is itself. And we did show that this integral equal to f of b minus f of a, which completes the proof of the second part of the theorem. So we finished the proof of the second part of the theorem. And now we are free to use this formula. We don't have to write down the limit of the Riemann sum again. We can just find one favorite antiderivative of small f and evaluate is f of b minus f of a. That's how we prove that. Now let's try to do some example. Example 1. D over dx. So integral from 0 to x sine square t dt. So this is exactly as the first part of the theorem, d over dx of this integral. d over dx of the integral 0 to x f of t dt. So that's the first part of the theorem. Recall that d over dx 0 to x f of t dt equal to f of x. And therefore, this one must be by the first part 1 of the fundamental theorem of calculus. This one equal to sine square of x. And we finish this first example. Now let's try another example. D over dx 0 to x square root t square plus 1 dt. So again, you have the form d over dx integral 0 to x something like f of t dt. This one, by the fundamental theorem of calculus, this one must be f of x. So this is the function f. We have f of x is square root x squared plus 1. Now let's try with another example. How about d over dx from x to 0 t squared plus 1 dt. Now I just copy exact function here, but I swap the bounds from x to 0 now. Remember that the fundamental theorem of calculus, you need to have d over dx 0 to x. Here I have x to 0, which is not the form that we can apply immediately. We need to write down again. D over dx still there. 0 to x now. We need 0 to x, and therefore I need to put the minus sign. Square root t squared plus 1 dt. So this is, you can put this minus outside. So this is minus d over dx 0 to x t squared plus 1 dt, which by the fundamental theorem of calculus, this one equal to minus still there, square root x squared plus 1. So which is this one. So remember that when you apply the fundamental theorem of calculus, you need to have the correct bound here, the limits from 0 to x. Let's try one more example. Example 4. What if now we have d over dx 1 to x cubed, no, x fourth, d over dx 1 to x fourth of secant of t dt. Okay, be careful here because the fundamental theorem of calculus tells us that the integral from 0 to x, this is we have x to the fourth. So warning that it is not secant x fourth. No, this is not that one. You need to have the form x here. How can we do it now? Now I want to change it to the correct form that we can apply the fundamental theorem of calculus. Let say u be x4. So this means let y be this one. So this means y now becomes d over dx let y be this one, what is here. So y be interval from 1 to x4 secant of t dt. Let u be this. Let y be this integral. Now d over dx of y becomes d over dx of y becomes dy over dx. This one can be written of the form 1 to u, because u equal to x to the fourth, secant of t dt. Secant of t dt dy over dx. Y is function in u. U is a function in x. By the chain rule, we have dy over du times du over dx. So dy over du, d over du of y, which is d over du of this one, times du over dx. Du over dx is dx4 over dx times dx4 over dx. We do derivative of x to the fourth with respect to x. The red part, d over du, integral from 1 to u of a function ft dt. By the fundamental theorem of calculus, this one is exactly similar at this one. D over d something du, 0 to u, ft dt. Here's f of x, so in between x to u here is f of u. So this is this function secant of u multiplies the green part is 4 times x cubed. And now I write down everything in x. Secant of u, secant of x to the fourth times 4 times x cubed. So I write 4 x cubed secant of x to the fourth. That is dy over dx. That is this one, d of this one over dx. So remember, whenever you have that, you need to use the chain rule. We can apply fundamental theorem if this upper limit is, say, x or u or anything here, but this one not x to the fourth. And then you need to do chain rule. Now let us try with the second part of the theorem. Say, can we compute integral from 1 to 3 e to the x dx? So we just need to find one antiderivative of this function, which in this case it is e to the x itself, because e to the x prime equal to e to the x. And we plug in for x from 1 to 3. This one, e3 minus e is 1, which is the answer. Let's do another one. Integral from, say, minus 1 to 3, 1 over x squared dx. Now look at this. This function 1 over x squared, you consider from minus 1 to 3. 1 over x squared does not, this function is not well defined from minus 1 to 3. So f of x equal to 1 over x squared is not defined at x equal to 0 on this interval, and therefore it is not continuous. Not continuous on -1, 3. And in order to use the fundamental theorem of the calculus, we need the function to be continuous on the closed interval we are working with. So in this case, we can't use the fundamental theorem of calculus. And this one, we will treat it later when we learn about improper integral using a limit. Improper integral. So be careful. We need to have the continuity condition. Now there is one difficult example here. This one is hard, a bit harder. Say find the value b of b bigger than -1 that maximize interval from -1 to b x squared phi minus x dx. Find the values of b bigger than -1 that maximize this interval. So we have an optimization problem. How can we maximize this one? This one is actually the area under this curve for x from -1 to b. And we want b here bigger than -1 for sure, and we want b here so that this area is maximum. How can we do that then? So remember that we have the first derivative test. Here b bigger than 1 on the interval -1 infinity. We have the function. Let me call this function f of b. It depends on b. This is a function in b. We want to maximize b. Find b such that f of b is max. How can we do that then? We compute the first derivative of f prime of b equal to this one prime d over db, derivative with respect to b of this interval. We have derivative of integral by the fundamental theorem of calculus. This one must be the function. So this one, by the fundamental theorem of calculus, this is b squared phi minus b. Fundamental theorem of calculus part 1. b squared phi minus b. We have f prime of b. We now can find the critical point. Critical point now, derivative exists for all b between -1 and infinity. Critical point is the point where this one is 0, equivalent to b is 0 or b equal to 5. We have two critical points. Now let's draw the chart or the table. We have b between -1 to infinity. We have critical point 0, critical point 5. F prime of b equals 0 here at critical point 0 and 5. Now we look at the sign. To make it easy, we can write the table like that. In this case, it's still easy, you can draw immediately. But to make it even easier, we can do this. Now I draw, say, instead of f of b here, I do b and phi minus b. b squared equal to 0 when b equals 0. And then I also have the second term, phi minus b. Second term, phi minus b equal to 0 when b equal to phi. Now, then we have f prime equal to 0 when b equal to 0 or b equal to phi. And then the last one is our function f of b, where we try to maximize. B square always non-negative. Phi minus b is negative, so negative here, positive here. So when b is bigger than phi, this one is negative. When b is smaller than phi, this one is positive. So on the left of these linear terms, you can think of that on the left of 0 is opposite at the side of this. So this coefficient minus 1, opposite as that plus 1. So plus sign and minus, same sign. Now f prime equal to the product of b squared times this. Positive must be positive here, and negative here. So we see that our function increasing, decreasing. This one will be the maximum. So from this table, we know that the maximum occurs when b equal to phi. F of b is max when b equal to phi. We consider the interval from -1 to infinity. Maximum at this point b equal to 5. So we answer the question. B must be 5, so that this one is max. This is our final answer.